Hello friends, with your support, I am able to prepare my sixth lecture for in machine learning series that is on principal component analysis. So first of all, we'll come to know that what is the importance of principal component analysis. What principal component analysis gives me the reduction of dimensionality of data. This is the output of PCA after applying on the Cipher 10 dataset. This Cipher 10 dataset, this consists multiple images of different classes and it consists 3027 features. So if you apply your principal component analysis to a high dimensional data, your data gets reduced and you'll be getting the output according to different categories. I'll be covering the PCA output in my subsequent slide. So, what is PCA actually? So, PCA is a statistical technique that is used to reduce dimensionality of data. So, for the large data set, it is very helpful. And as you reduce the information, as you extract the important information, definitely your size of number of features will be reduced. So your data, the complex data will be simplified and you can plot your features rather than having many different axes. You can plot your features by PCA on two axes only. That is giving you the maximum variance in data. So we will cover this in subsequent slides. So why PCA is important? PCA is, as I said, you can plot your multiple features in two axes or more than two axes. So this is the outcome of MNIST data set. So MNIST data set everyone is familiar of. This is of digit data set and this is black and white. This has 10 categories. My data is available in 10 categories. So I'm having 10 different digits that is 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. All of my category, all of my digits are represented by these colors. So we are having total 10 clusters in this output corresponding to each digit present in my data set. As I said, the principal components are nothing but they are giving me the variance. So where we are having maximum variance that we used to plot on x-axis and the next variance, which is next maximum variance after this, we'll plot on y-axis. So this is my 9.56. This variance is 9.56. This variance is 12.03. And these variants are nothing but are your eigenvalues. These variants, what we are showing, these are the eigenvalues. So this is your lambda 1 and this one is your lambda 2. So if you plot you need to remember two things here. Whenever you plot the output of PCA, you will be getting as many clusters, as many categories you are having in your data set. So here this is a data set of 10 disease. So you'll get 10 different clusters of your data and your axis will be the eigenvalues, the maximum eigenvalue, then next maximum eigenvalue. Likewise, we used to plot the output of PCA. So now let us see how PCA works. So PCA is used for reducing the dimensionality. As you are reducing the dimensionality, your model works fast. Definitely, you have less number of variables, So the model works fast and it will be efficient and will be reducing the curse dimensionality. So we'll see it in subsequent slides. I can visualize by PCA. This is a plot for iris dataset, which is the output of PCA for the iris dataset. Because iris dataset consists of three classes, that is Setosa, Vesicular, and Virginica. So corresponding to three clusters, we are getting three clusters, and there are four features present in my iris data. So these features are basically overlapped on the categories found by the principal component analysis. Then by the principal component one, we are able to get 92.46 variance in principal component 1, that is maximum variance we are getting in the first principal component. The next variance we are getting in PC2, that is principal component 2, that is 5.1 is the variance of my y-axis. So we'll see how this works. First we'll see how it works. So I'm skipping this slide. We can use PCA for data compression and removal of noise. So if I reduce the principal component 2, then my data is reduced because it is giving me the less variance, whereas the principal component 1 is giving me the maximum variance, that was 94%. For removal of noise pixels generally they are having high variance data. So if I remove the high variance one, I can remove the noise. Again, it can be helping in the image compression. So if you plot the output of images after reducing by the PCA, then you can see that the principal component one consists of the maximum information, or the lower principal components are giving you the maximum information. So you can leave the higher principal components to reduce the dimensionality of your data. So first we'll do the calculation, then you'll come to know how PCA reduces the size of data. Now, let's take an example of a 2D data set. I have five different uh, values of my data. So this is, let's say this is x1 and this is x2, or I can say x and y. So let's say this is x and this is y. So if I plot this, I'll get this first data point, that is 2, 4. This is my second data point, that is 3, 3. Then this is my third data point, that is 4, 2. Then fourth data point, that is 5, 5. And we have the sixth data point, that is 6. So you can see the how my data is varying. That's my original data. So for calculation of PCA, for getting the principal components, what I need to do is, as my uh, step 2, I need to center the data. For centering the data, what you need to do is, you need to subtract the mean of data from every value present in the column. So I'll subtract mean of the data. Mean of x1 is 4 and my mean of x2, or mean of x is 4, mean of y is 4 here. So if I subtract this mean, my data got centered. And if I plot my centered data, you can see there are certain values goes to the negative axis of x, and so there as well as positive axis of x. Say for y, my some values goes to the negative axis of y, as well as some value goes to the positive axis of y. So this is called my centering of data. So now my center is shifted to 0. So after doing the center of data, then you need to calculate the covariance of this centered data. So for calculation of covariance of this centered data, you need to multiply the transpose of the centered data into the uh, tra- original form of my center data. This will give me the covariance matrix. Covariance matrix is written as this is variance of x, covariance of xy. This is covariance of yx and variance of y. And this is a square matrix. Covariance of x, y is equal to covariance of yx. As you see, this is 10 and this one is also 10. Variance by chance we are getting as same, but it's not mandatory, you'll get the variance as same. So um, if I divide, I need to divide this by n minus 1. So that is my number of data points. So I'll get the variance as 2.5 is my variance of x. So my variance of x is 2.5. Variance of y is 2.5 again. Then covariance of y, and that is equal to covariance of yx is equal to 1.5. Okay, so this is how I can get the covariance matrix. After getting the covariance matrix, I need to calculate the eigenvalues and eigenvectors of this covariance matrix. So for eigenvalue, what I need is I want determinant of A minus lambda I is equal to 0. This is my A matrix. So if I do determinant of 2.5 minus lambda 0, 0, sorry, not 0, 1.5. This is 1.5. This one is also 1.5. And 2.5 minus lambda. This determinant of this is equal to 0. So you are having 2.5 minus lambda into 2.5 minus lambda minus 1.5 into 1.5 is equal to 0. So this gives me values of my eigenvalues. If you solve this, the values of my eigenvalue is 4 and 1. And then what I need to do is for eigenvectors, I need to substitute in this equation all my eigenvalues. So what I'm having for the first eigenvalue, I'll be having A of V is equal to 4 of V. For this second eigenvalue, I have A of V is equal to 1 of 1 of V. V is nothing but is a vector. I need to assume I don't know this vector. This vector I need to identify. So V1 basically, V1 I got as 1, 1 and V2 I got as minus 1 on 1. And to before transforming my data, what I need to do is I need to convert this to unit vector. So for converting this as unit vector, this is basically my unit vector. Converting it as unit vector, what I need to do is 1 divided by under root of 1 square plus 1 square. This will give me the unit vector. So the vectors written here, they are the unit vectors of V1 and V2. So this is the unit vector of V2, this is the unit vector of V1. So once I get first step, what I have is I need to plot the data, then you need to center the data. After centering the data, you need to calculate the covariance matrix. From the covariance matrix, you need to calculate the eigenvalues and the eigenvectors. Then you need to convert your vectors into the unit vector. So after converting the unit vector eigenvectors to the unit vector, then you need to arrange your vectors according to the highest eigenvalue to lowest eigenvalue. So then next step is I can say 4.5. This is sort eigenvectors, sort your eigenvectors according to highest eigenvalue. So this one is corresponding to eigenvalue 4 and this one is corresponding to eigenvalue 1. First, I'll have to put the eigenvector which is corresponding to the highest eigenvalue. Then I need to put the eigenvector which is corresponding to the next eigenvalue. So I need to form a matrix of eigenvectors, all eigenvectors, what I receive. And then for to get the projected data, this last step, I need to project my data. So to get the projected data, that projected data is nothing but is the data what I shown as piece output of PCA. So to get the output of PCA, what you need to do is you need to multiply this center data with the matrix what I received by the eigenvector, by the unit eigenvectors. So these are my unit eigenvectors. So if I multiply uh, these with the center data, I get the projected data. So now if I plot this projected data, so if you plot this projected data, you can see this if now I'm having my data points as there are certain value again at the negative side, there are certain value at the positive side, and this data is the x-axis, is this x-axis is called my PC1 and this y-axis is called my PC2. So this PC1 is corresponding to the eigenvalue 4, that is highest eigenvalue. This one is my highest eigenvalue. And the variation of PC1, the variation of PC1 is equal to, this is also variance of PC1 and this one is variance of PC2. You need not to calculate the variance. So you see the span of this one, the y-axis, the PC2 is lesser than the span of PC1, that is my principal component 1. This is my principal component 1. So principal component 1 will give me the maximum information that is that we have seen in case of iris dataset that was 94%. So 94% is the majority of data points are already covered, whereas the rest one is giving me 5 point something percent, the PC2 is. So I can leave this component, how my data is being reduced is, I can leave this component PC2, I can keep only the PC1. So if I keep only PC1, my data set is reduced. So this we are doing for two data only. As many features you are having in the your data set, that many principal components you will receive, and as you go down in your principal components, your variance is being reduced every time. Like in case of images, it is possible that your PC1 is having the 66% information, then PC2 is having like the 30% of information, then PC3 may be having uh, 5% of information, then PC4 may be having some 3.1% of information. So likewise, if I take this PC1 and PC2, this will cover my maximum information is being reserved in these two. So for the compression, what we do is we used to leave this PC3 and 4, and I'll keep only the higher principal components so that I can retain maximum information, and I lose minimum of that information. So that is how my data is reduced in case of principal component analysis. So if we say PCA in nutshell, first what you need to do is you need to plot your data, then you need to center your data, then you need to calculate the covariance matrix. After getting the covariance matrix, you need to calculate the eigenvalues and eigenvectors. Next, you need to arrange your eigenvectors according to highest eigenvalue. Then you need to transform your data according to the highest eigenvalue to the lowest eigenvalue. And lastly, you get the projected data. And if you see the projected data is having maximum variance, this E is nothing but is corresponding to the eigenvector 1. This is corresponding to, so this is my principal component 1. This one is my principal component 2. So again, if you see the variations, the variance of this axis is much higher than the variance of this one. So this is covering at least more than 90% variance of my data. So I can keep PC1 only and PC2 can be removed because there is very less variation in this direction, in y direction. All I'm having in the x direction. So this is how your PCA works. Why we should use PCA? PCA is used to simplify the data for making model interpretable and efficient. You can visualize your data, you can do the data compression, you can reduce the features, and there are wide variety of applications of PCA. We are using it in computer vision, we are using it in finance, genomics, natural language processing. That's all about PCA. Thank you very much. If you like my videos, please hit the like button. Or if you have any queries, please feel free to ask me the questions. You can write in comment box, you can email me, or you can personally solve. If you like the video, please share to your friends. Thank you very much.